Hi guys, welcome back. So today we'll be discussing a new part of our physical chemistry lecture series. Previously we discussed equations of state, so now we'll be looking at the bigger picture of thermodynamics. So our approach to this topic will be by law, namely we'll be discussing thermodynamics starting with the first law, which is concerned with the conservation of energy, followed by the second and third laws, and then with a discussion on Gibbs free energy. So let's just start with some definitions. Okay, so first let's define thermodynamics. Okay, so traditionally, thermodynamics has been defined as a study of energy and its transformations. Okay, so you could see that from the name. Okay, so thermo relating to energy and dynamics relating to transformations. In the bigger picture of thermodynamics, however, we could also define it as the study of restrictions on the possible properties of matter or on permissible physical processes. Okay, so thermodynamics, it pretty much tries to establish relationships between the different properties of matter and the way that these properties can be changed after undergoing processes. So recall in our discussion of equations of state, we wanted to establish relationships between pressure, volume, temperature, and number of moles of a system. So we're pretty much describing the properties of matter in a particular state, right? So in the larger picture of thermodynamics, however, we want to relate all the parameters of the system, including its internal energy, entropy, as well as its other properties that we just mentioned. Okay, so why do we want to do this? We want to do this so that we could describe and make predictions about the behavior of a system in terms of its energy as well. So we could start looking not only at the properties of matter, but also the processes that matter undergoes. Okay, so we're going to be looking at changes in the state of matter before and after a process. Okay, so while the study of thermodynamics can get a little bit abstract, in these abstractions of these concepts, we find that we could apply them in many cases. Okay, that is, we have universality. So it pretty much applies to all systems. So the laws that govern how machines and engines run, for example, are the same that governs the reactions that fuel stars, and even the laws that govern biochemistry and biology. Okay, so the laws that govern life. Okay, so thermodynamics is a very universal field of study. All right, so before we start, let's proceed with some definitions. In studying thermodynamics, we want to divide the universe into two parts, okay, namely the system and the surroundings. Okay, so the system, this is just part of the universe under study. Okay, so the rest of the universe that's not in the system is just called the surroundings. Okay, so we can divide our system from the surroundings using a wall. Okay, so the wall is pretty much a barrier, and the type of wall that we use defines the system's so-called boundary conditions. Okay, so let's look at different types of systems that we can have. Right, so if we have a wall that is both permeable and diathermal, we will have an open system. Okay, so an open system is characterized by a free exchange of matter and energy. Okay, so living organisms, they are open systems. Okay, so we breathe out and breathe in air, for example, and we could easily exchange heat with our surroundings. Okay, other types of systems include a closed system. Okay, so if our wall now becomes impermeable, okay, so we no longer have an exchange of matter with our surroundings, but we could still exchange energy. Okay, so most of the simple systems that we'll be talking about in our thermodynamics discussions will be closed systems. Okay, so we won't be seeing any change of the amount of matter in our systems for a closed system. Right, so another type of system is an isolated system. Okay, so now our wall is going to be impermeable and adiabatic. Okay, so there's no exchange of both matter and energy. All right, okay, so let's now look at different types of properties of a system. Okay, so overall a property, this is just a macroscopic observable that defines the state of the system. Okay, so we have two major types of these properties. Okay, so we have extensive and intensive properties. Okay, so extensive properties are just going to be dependent on the amount of matter present. Okay, so for illustrative purposes, let's have this system that is divided into four parts. So overall, if a property is extensive, if we take the property of part 1, part 2, part 3, and part 4, and we sum them all together, okay, the sum of that is going to be the property of the entire system. Okay, so mathematically we could express this as the following. Okay, so property X is an extensive property, so that means the sum of the property of part 1, part 2, part 3, and part 4 is equal to the whole. Okay, so examples of extensive properties include volume, internal energy, enthalpy, entropy, and number of moles. Okay, so we could easily see this with volume. Okay, so if we take the volume of 1, 2, 3, and 4 and we sum them all together, okay, that would give us the total volume of the system. All right, so we also have another type of property, which is the intensive properties. So intensive properties are going to be independent of the amount of matter present. Okay, so again, for illustrative purposes, let's take this system that's divided into 4 parts. Okay, so if we have an intensive property, okay, so if we measure the intensive property of part 1, 2, 3, and 4, okay, they're going to be the same as the property of the whole. So this is going to be in contrast to extensive properties that are additive. So to express this mathematically, okay, so the intensive property of the total system is going to be equal to the intensive property of part 1, part 2, part 3, and part 4. Okay, so that means you could just measure the intensive property of one part of the system and you pretty much get the intensive property of the whole system. Okay, examples of intensive properties include temperature, pressure, density, and molar quantities such as molar volume, molar enthalpy. Okay, so we could use temperature as an example. Okay, so in this particular system, okay, if we measure the temperature in part 1, 2, 3, and 4, the total temperature of the system is not going to be the sum of the individual temperatures that we just measured. Okay, so actually the temperature should be the same in all of these parts of our system, and the temperature of the entire system should also be the same as those taken from the parts. All right, so that is an intensive property. All right, so those are just some terms that we wanted to define before we proceed with our more formal discussion of thermodynamics. Okay, so of course, when we start talking about thermodynamics, there's also another thing that we need to define before we go into anything else. That is, what is energy? We use the term energy a lot in everyday life, but of course, what is it exactly? Okay, so a lot of textbooks define energy as the ability to do work. Okay, so of course, when you analyze this definition, you start to wonder, okay, what does it mean to do work? Okay, so when we look at the definition of work, however, work is also defined as a method of energy transfer. Okay, so this definition is kind of circular because if we look at this, we're pretty much defining energy as the ability to transfer energy. Okay, so not very informative. Okay, so another definition that we could use is this one by Dave Watson. Okay, so Dave Watson defined energy as a property or characteristic of matter that makes things happen, or in the case of stored or potential energy, has the potential to make things happen. Okay, so by making things happen, we are causing changes. Okay, so changes in properties of our system, like changing the temperature, changing the pressure, changing the volume. Okay, so this is due to energy. Okay, so this is what we're interested in thermodynamics after all. Okay, so we're interested in analyzing changes in the properties of our system after undergoing processes. Okay, so all of these changes are driven by energy.